Hey guys, we're going to talk about similar polygons today. A lot of this might be review, so if it is, then great. If not, this will kind of give you a brief overview of what we're going to do this chapter, and that is talk about polygons, in particular triangles. We'll get into triangles in the next section, but how polygons can be similar and what makes them similar. Alright, so the first thing we're going to talk about is the definition for similar polygons. So I'm going to highlight that, and if you have a highlighter you can follow along with that, or you can do it later, that's fine too. So the definition for similar polygons is polygons that have a correspondence between angles that are congruent. Yes, I did say their angles are congruent. It is weird how that works out. Angles are always equal from one similar polygon to the next. Even though the polygons don't look the same, their angles are the same. But their lengths, the lengths of the sides, they are proportional. So corresponding sides are not congruent, they are proportional. You can kind of see down here an example of that. You can see that the sides are definitely not congruent. Okay, but we're going to find that the angles right up here, we're going to find that the angles right up here are congruent. This angle and this angle are exactly the same. But let's talk about scale factor for a second, because that is a huge deal. All right, we talked a little bit about ratios in the last section, and that's what a scale factor is. It is a ratio, all right, a fraction. And to make this fraction, all you take is the lengths of two corresponding sides. So let's look at the example right here. Suppose you're asked to find a scale factor for the following enlargement. And you've got a picture here that's a 4 by 6, and up here you see the same picture, but it's 6 by 9 instead. So we need to figure out what is the scale factor. In other words, how big did this picture get? How many times bigger is it? Now things can get smaller also, so beware of that, and I'll show you how to do that as well. But if we're going to do an enlargement and we want to figure out the scale factor for that, then to do the enlargement you always put the big number over the small number. And that will give you an enlargement, and that gives you the scale factor. And honestly, we just need to compare two sides, because the other sides will be the same proportion. So I would put 9 over 6. And of course that reduces to 3 over 2. So this is my scale factor. Now it might make better sense to you if you change that to a decimal. So 3 divided by 2 is 1.5. That means that the picture is actually 1.5 times bigger than it was before. Now, honestly, we really like the fraction form of that, but the average person off the street really likes the decimal version. And even better yet, if I go to the copy machine and I want to make my picture bigger, the copy machine does that in percent form. So that would be 150%. Because if you remember right, you have to move that decimal over 2 places to make the percent. So keep that in mind when you're doing enlargements and reductions, is that they can be given as fractions, decimals, or percents. But we're probably going to stick with the fraction version of it, just because it's a little easier to use. Now, that did say enlargement, but just for the sake of it, I'm going to talk about a reduction. Let's say what we did instead is we reduced the size of this. If we reduce the size of this, then what we want to do is we want to put the small number on the top and the big number on the bottom. And in which case that's going to make it 6 over 9, or 2/3. So that's going to be 2/3. Let me just put a little line in here to separate that so it doesn't get confusing. That's going to show that our picture is 2/3 the size it was before, 2/3 of its original size. So a decimal for that is 0.6 repeating, and if we wanted to change that to a percent, move that decimal over 2 places to the right, and we have 66.6 repeating percent. So if I go to the copy machine and I want to make my picture smaller, then the copy machine is going to ask me what percent do I want. So I put in about 67%. I don't think there's too many copy machines that do decimals. So I'd put in 67% of the size, and so it will tell it what to reduce it by. All right. So that explains how to do reductions and enlargements. Let's make sure we understand scale factor. I think I mentioned before that the scale factor is how many times bigger or smaller it is. But here you can kind of see that. If I want to get bigger, then I want my scale factor here to start here, and I want to multiply by a number greater than 1. All right, this is greater than 1. Because 1, remember, is 100%. And that's not going to change it at all. If I go to the copy machine and I say make it 100% of its size, it's going to be exactly the same as it was before. Okay, they are congruent. So what I need to do is make it just slightly bigger. So I'm going to multiply by a number greater than 1 on that copy machine. Or tell the copy machine 150% to make it bigger. And where did I come up with that number? I took the size that I want, and I divided it by the size that I have now. The size I want divided by the size I have. And that'll tell me what I need to multiply by. So 9 divided by 6. In other words, big number over small number. That will give me my scale factor. Now, if I'm going to make it smaller, then I'm going to put small number over big number. Okay, it's still the size that I have over the size that I want. So 6 over 9, that gives me the 2/3. All right, well anyway, these are the scale factors. And of course, if you're going to go as a reduction, you are going to find a number smaller than 1. And that will make a reduction in size. All right, let's do these last couple examples real quick. The first one talks about all you have to do is decide if the polygons are similar. If they are, write a similarity statement. Seriously, you have to check every single side, all right, to make sure that they are proportional. You can see that the angles are going to definitely be equal. You don't really have to check the angles. All you have to do is check your sides. So I'm going to look to see which side goes with which side, because I got to stay corresponding here. So I'm looking and I'm thinking that AB goes with EF. So I want to make sure that AB over EF is the same as AD over EH. AD over EH. And I want to make sure that's the same as DC over HG, because they correspond to each other. And lastly, BC over FG. Now notice I did big over little, big over little, big over little, big over little. All right? If I'm checking to see if they're similar, it doesn't matter which number you put on the top. If I decide I want bigs on the top, I put bigs on the bottom. Put littles on the top. Bigs on the top and littles on the bottom. If I want, I could put all the littles on the top and all the bigs on the bottom. As long as those fractions are equal, I know that I have similar polygons. So let's check them. Let's see, the first one's 10 over 5. Does that equal 18 over 9? So far, so good. They're both 2. What about 22 over 11? Yay, I'm still equal to 2. What about 20 over 10? Woohoo! They're all equal to 2. and I know that they are similar. So yes, they are similar. Now, since they're similar, I can write a similarity statement, and so what I would say is A, B, C, D is similar. And notice the similar statement doesn't have an equals under it. Don't make it congruent. Make it similar. A, B, C, D is similar to E, F, G, H, because the A goes with the E, the B goes with the F, the C goes with the G, and the D goes with the H. Alright, so here's my similarity statement. Alright, so that could be switched around here, but make sure you switch it around here also. Next example, find the value of x and y in the figures below. Now, remember we said before, angles are congruent. The sides are proportional. So I gotta turn this little guy upside down like this. I gotta turn it upside down so that the right angles are the same. It just gets a little confusing upside down like that, but let's see if we can't make it work. We can see where the 1/16s are. So that probably means that this y minus 73 probably goes with this angle right here. This is probably y minus 73 degrees also. Alright, now what do we know about the angles on the inside of a quadrilateral? Well, we know that they add up to 360. So I know that 61 plus 90 plus my y minus 73 plus my 116 better give me 360 degrees. Now don't assume that this is a right angle. Okay, you can't assume that. That's using the eyeball postulate, and the eyeball postulate is not a good idea. Let's go ahead and solve this. Let's see, we've got 151. Y minus 73 plus 116 equals 360. So I'm going to get my calculator out here so I don't make any mistakes. Minus 73, you can see that, plus 116, and looks like I have 194 on this side. Let me double check that. 151 minus 73 plus 116. Okay, now I'm going to subtract 194 from both sides. Now I'm going to cheat a little and go ahead and subtract 360. But I'll have to remember my answer is positive. Alright, it's just the way I cheat a little bit so that I don't have to take that number out of my calculator. So I subtract 194 from both sides and I get 166. So the answer is 166, and that gives me y. Let's see here. Now my x is not 5. Clearly this line is shorter than this line. But I have to figure out what is the proportion here between the sides. I can use these two sides to tell me because they correspond. So I know that 4 is to 6 like 5 is to x. So I can write a proportion with my sides. 4 is to 6 like 5 is to x. Have you ever heard the hand is to glove like foot is to shoe? That's the way proportions do. 4 is to 6 as 5 is to x. And so I just cross multiply. 4 x's equal 30. Divide both sides by 4. 30 over 4 equals 15 over 2 equals 7.5. And there is my x. You could just leave it 15 over 2 if you wanted. Alright, and that would be just fine. And that is the lesson for today. Great job, guys.